Okay, looking at Module 13, we're going to study some log properties. As we've been defining what logarithmic functions are, we talked about logs in our previous section as we defined exponentials. Exponentials and logs, remember, are inverses of each other, and we learned that logarithms are exponents. Our definition shows that here as we're looking at log base a of x equal to y. We know, again, our base a needs to be a number greater than 0, not equal to 1. And, of course, what we take the log of needs to be greater than 0. And it equals some number y. And, of course, y is the power to which you raise your base to get what you're taking log of. So, yeah, log base a of x equals some number y if and only if a to the y power is x. So let's x, y, and a be real numbers. With a greater than 0, not equal to 1, our restriction on our log base, and same goes our exponential base, a to the x, that we studied in our previous section. And x needs to be greater than 0, just to take care of our restrictions with logarithms with the domain variable. And y needs to be greater than 0. And those are restrictions if we talk about our exponential model. We talked about with a to y equal x, right? That's a restriction on the exponentials. With that said, it says here in our first property that the log of 1 doesn't matter the base. It can be any number greater than 0, not equal to 1. It's going to always equal 0. And that's true. And we know why, again, based off our exponential property. We know that a raised to a power 0 will always equal 1. Right? We raise anything to a power 0, that number is greater than 0, not equal to 1, it's going to have an output of 1. So yeah, log base 2 of 1, it simplifies to 0. Log of 1 simplifies to 0, right? Now log base e, remember, is the abbreviation, right, for natural log. And just like this is log base 10 of 1, yeah, 10 to the 0 power is 1. All right, property 2 says if we have log base a and we take the log of a, so we have that same number, a, we know that its output will always be 1, simplifies to 1. And that's true because a raised to the 1 power will give you a, right? What power do you raise your a to get a back? 1. So yeah, log base 2 of 2 would equal 1. Natural log of e, which is log base e of e, that would simplify to 1. Log base 10 of 10 would simplify to 1. So again, that doesn't matter. Again, those bases are identical. It simplifies to 1. Now, say we have property 3, we get into our composition properties. All right, composition of inverses. So we're going to put an exponential into a logarithm, which we know they're inverses of each other, as we talked about in our previous section. Well, based off the inverses, we know that it's going to always simplify to x. So here we got log base a of a raised to the x power. What does it equal? X. All right, so again, that's the exponential plugged into the logarithm. So again, based off characteristics, right? F composed with F inverse, so always simplify to x. Remember our symmetry line of y equals x. So if we take log base 4 of 4 to the x power, it's going to simplify to x. Just like natural log of e to the x. Well, natural log is log base e. Yeah, log base e of e to the x power is going to simplify to x. Log base 10 of 10 to the x power is going to simplify to x. And I like to think of those as my washout rules. Whenever the bases are the same, right, they're going to wash out, and it simplifies to whatever you have there in your exponent. All right, so let's go ahead and take that property and apply it to exponentials with logs plugged into it. So here I've got an exponential base a, a logarithm with the same base, a to log base a of x. Well, again, that's going to simplify to x based off composition of inverses. So again, they're the same basis. So 3 to log base 3 of x is going to simplify to x. E to the ln, that's e to the log base e. Well, it's going to simplify to x, whatever we're taking the log of. 10 to the log base 10 of x simplifies to x. So looking at example A here, log base 15 of 1. Well, what does it simplify to? We know the log of 1 will always equal 0. It doesn't matter the base. And we could check it, right? 15 to the 0 power is 1. Yeah, the power which raise our base 2 to get x. That's what that log equals. Property here in B is log base A of A property. Should simplify to 1, right? Log base 7 of 7. These are identical. So again, you can think of it also as our property we mentioned with compositions, right? Log base 7 of 7 to 1 power is 1. Log base A of A to the x is x. So again, different ways to look at that, but again, those are the same, so it simplifies down to 1, and we can check it. Yeah, 7 to the 1 power is 7. Yeah, that's what our log value equals, is 1. Power which raise our base 2 to get x. Same thing going on here in example C. Log base 2 of 2, same basis. Well, whatever we have here in the exponent is what we're going to be simplifying to. Simplifies to x plus 2. Yeah, 2 to the x plus 2 power equal to the x plus 2. How about example here in D? We got 5 to the log base 5. These are identical, so it simplifies to 4x minus 3, right? They wash out. All that's left is what you're taking log of. Same base rule here in E. Log base t of t. Well, it simplifies to 27/13. They wash out. That's all that's left. E to the ln of y to the 5th power. Well, that's equal to e to the log base e, if you want to rewrite it. Same basis, so it simplifies to whatever we have there is what we're taking log of. So it equals y to the 5th power. Natural log of e. Well, that's log base e, right, of e. So they're going to wash out. So these are the same. So it simplifies to whatever's there in the exponent, x plus 2. So there's some simplifying properties that we want to be able to recognize. And like I said, and eventually we're going to get to solving log equations. And we want to be able to simplify our expressions that show up in our equations. So those are things to look for to help us in simplifying so we can evaluate and solve logarithms. Moving on, let's go to our 3 major properties. I call them our major properties of logarithms. That being the product rule, all right, the quotient rule, and the power rule. Now, the product rule states that we can express a single logarithm as a sum by looking at the factors of what we're taking the log of. So if we have a product, for this example, we're multiplying m and n together. It says log base a of m times n is equal to log base a of m, so log of the first factor, plus log base a of n, the second factor. So it creates a sum of logarithms. So however many factors we have is how many logs we're going to have in that sum. We're going to take the log of each factor. So I'm going to simplify using our product rule. So we had log base 2 of 8 plus log base 2 of 4. Well, using the product rule, since these are the same bases, we can add these together by multiplying what we're taking the log of. So here I am going from log of m plus log of n over here to log of m times n. So there's log of 8 times 4. So log base 2 of 32, right? And that we could evaluate. What is log base 2 of 32? It equals 5, right? Because 2 to the 5th power is 32. Right? Now, you could also get there, right, looking at these logs individually. So just to show you this property, what's log base 2 of 8? 2 cubed is 8, right? So it's 3. What's log base 2 of 4? 2 squared is 4. So again, what's 3 plus 2? It equals 5. So you see it over here used with the product rule. So I use my product rule to simplify this logarithm. All right, now let's look at the quotient rule. Now the quotient rule says we have a fraction like m divided by n that we're taking the log of. Well, we can break that up into a difference of logs. It says log base a of m divided by n is equivalent to log base a of the numerator m minus log base a of the denominator n. So quotient rule is log of numerator minus log of the denominator. So let's take that and apply the quotient rule. So we look at using the quotient rule, let's go to an example. Let's find the value of this expression. Let's simplify together. So here's log base 2 of 16 minus log base 2 of 4. Well, they're the same bases, so we can combine these together. Now we subtract logarithms by dividing. So it's going to be 16 divided by 4. So again, I'm taking this log of m minus log of n, combine it into 1, log of m divided by n. So that's log base 2 of 4, right? 16 divided by 4, which is equal to 2, right? 2 squared is 4. So using the quotient rule, log of m minus log of n equal log of m divided by n. And we could show that just working it out step by step. You know, we all know log base 2 of 16 is 4 because 2 to the 4th power is 16. We also know log base 2 of 4 is 2, and 4 minus 2 is 2. So you can see that both ways. But I like, again, showing it with the quotient rule. So there's ways we can use the quotient rule. What's the quotient rule allow us to do? It allows us to subtract logarithms. We do that by dividing what we're taking a log of. And remember, product rule allows us to add logarithms. They're the same basis. We can add them by taking the product of what we're taking a log of. All right, let's go to the power rule. Now, the power rule states you can form a product. So product rule forms a sum. Quotient rule forms a difference. And the power rule, like log base a of m raised to the p power. So here's my power on my exponential term. Well, the power rule states that this power comes out in front as the coefficient of your logarithm. So it'll be p times log base a of m. So you can form a product by taking down the exponent, bringing it out in front, or vice versa. We could put it back up into the exponent if we had a product. So let's simplify using the power rule. How about log base 2 of 4 squared? Well, applying the power rule, here's our power, right? We can bring it out in front. So that's equal to 2 times log base 2 of 4. And we know that's equal to 2 times 2, right? This is equal to 2 because 2 squared is 4. So we end up with 4, right? We could also show that using what we learned today, right? We could also simplify this. Log base 2 of 4 squared, of course, is log base 2 of 16. And yeah, we know 2 to the 4th power is 16. So just showing you that way. But I wanted to show it with the power rule. Right? The power rule allows us to simplify. So power rule allows us to form a product. All right, so let's go ahead and look at finishing off this set. Let's take some examples and sort of put these properties together here in the examples A and B. It says write each expression as a sum or difference of logarithms, express powers as factors, and simplify completely. So log base 5 of 25 times x squared. Well, again, we've got a product. We've got a couple factors. So let's go ahead and use the product rule. All right, let's go ahead and take log base 5 of 25, the first factor, plus log base 5 of x squared. Well, again, as we simplify, log base 5 of 25, that equals 2, right? We know that 5 squared is 25. So I went ahead and simplified that. Plus log base 5 of x squared. Well, here I could use the power rule, right? We know the power rule can be applied here. So let's use the power rule. And let's go ahead and bring down that power. So the product rule created my sum. And now I'm going to use the power rule. That's 2 times log base 5 of x. So simplifying down, we've created a sum and, of course, a product within the sum using the power rule. So product rule allows us to create a sum of logarithms. Right, and then we were able to break that down a little bit with the power rule. But that's all the properties we can apply. Let's take example B and let's break it up using our properties. So here I've got a fraction. So we can use the quotient rule. So quotient rule allows us to create a difference of logarithms. So here we got our m, right, and our n, so to speak. So log base e, the natural log of the numerator, minus log base e, or natural log of the denominator. So we got natural log of x right, minus natural log of e to the x. Now, natural log of e to the x, let's simplify, right? That's one of our properties. All right, we want to simplify that. So remember, log base a of a to the x power simplifies to x. So yeah, natural log of e to the x simplifies to x. Right, so that equals x. So here we are simplifying down using our quotient rule. Right, and one of our simplifying properties, the same base property. So this examples, again, applying these properties. We'll continue to use those in our next few examples.